Today, our lesson will cover linear regression, which you learned in high school. Linear regression can be considered the ancestor of prediction, meaning we can use mathematics to describe the act of prediction. For example, in linear regression, you already have a preconceived notion that there is a linear correlation between two data points, psi. This linear correlation, if we look at our code, you might imagine there should be a line, and this line is often referred to as the slope. It has an input, which is x input, and then this is the output. Why do we see it this way? It's because the more time you invest, the higher your grades. This is the linear relationship we imagine. But is it possible that it could be reversed, meaning it might not necessarily be linear? It could be an inverted U. Why do we say this? You might have a learning curve where, as time increases, your grades are high, but as you become less focused, even with a lot of time, your grades might fluctuate like an inverted U. So, in prediction, if you start with a preconceived notion that your input and output have an imagined linear relationship, you can write this linear relationship into the program. This type of prediction is the oldest form, where we first keep the mathematical model in mind as you've already thought about it. If the data you collect today isn't as neat, not exactly X to Y like an invisible line, it might be a U-shape. If you insist on using this linear model y equals x plus b slope to fit it, then you'll find that its predictions are inaccurate. So before machine learning, predictions were based on mathematical formulas. Let's move on to basic regression, the earliest form of regression. To find this line, you first need to know this line, starting from drawing this graph. How do you define the description of this line? We say the x-axis is the input, the number of study hours, and y is your output, which is your grade output. To define this line, you only need 2 points. So you can say y equals x plus b, where a is the slope and b is the intercept. This is the basic formula for linear regression you learned in high school. If I already have this preconceived notion, meaning I've already thought about this model, can I use the collected data points to fit this slope and my intercept to estimate the parameters? Then I continue to input the known study time, maybe input 7, and it will predict the grade you might achieve. This prediction is based on having this bias value beforehand, and you assume that the sample you have won't change the level of fit of the model. What does it mean that it won't change the level of fit? It means that the distribution of the sample won't change, so you would say this prediction is very accurate. However, if your sample changes to another person, and this person might be very inattentive, studies for a long time, but still scores low, they might fall far from this line, possibly ending up over here. So at this point, your sample is something you've never seen before and doesn't lie on this linear distribution, making your prediction inaccurate. This is the oldest form of prediction, using mathematical concepts to think before AI existed, a kind of logical thinking that once occurred. All right, let's try it out. First, we copy to draft and bring it back. After bringing it back, you'll know that this code becomes yours. Once it becomes yours, you can modify it here. This section was once a sample because I knew I wanted to create something that truly had a linear regression form. But if I now deliberately do something like turning this XY into what I mentioned, it might look like an inverted U. I'm telling everyone I want to conduct an experiment for this point. All right, let's see. If I turn it into an inverted U distribution, you can imagine what an inverted U means. It means as time increases, you might score very high at a certain hour, but as you continue to increase, your focus decreases. So the score doesn't go up, but rather drops down. At this point, if you still force this data set to use a linear model for prediction, you'll be very inaccurate. So in this situation, as mentioned, if I first observe the distribution of the data, can we combine from this plane's curve graph, straight line graph, or multiple curve graphs to form its possible model distribution? This is how we thought about prediction before AI existed. So at this point, it creates a quadratic curve for us, and it's inverted. Now I will tell it that I want to keep the original SY linear distribution data points. Additionally, another set of U-shaped data points to compare the two data distributions. So at this point, I keep both because why didn't I accept it just now? Previously, when I demonstrated, I would directly accept it because here red means I would delete it. Then I would directly change it to keep the quadratic curve. So at this point, I want to keep both the linear and quadratic curves and observe them together. If your sample is different and you only use one model to approximate a distribution that doesn't match your model, what will happen? I want to keep this comparison, so I told it that I want these two things to exist on the screen at the same time, so I just kept it. Originally, the behavior that should have been accepted was ignored, and then I told him to continue helping me make changes, so at this point, we still need to come back and take another look. So at this point, he deletes this explanation, and then he says, this is a linear curve. At this point, he will have the original data linear curve, okay. But here, he didn't help me put the quadratic curve and the linear curve together. So I told him I want the two graphs overlaid. I don't want them separate. I want them overlaid. So if you can understand the code, you can check what you want to do, overlay the data of the two graphs on the same graph for comparison using two different colors and two different model borders. Overlaying them might look better. So at this point, I still don't accept his suggestion because I know what he did isn't what I want, because he separated the linear and quadratic curves. At this point, he will distribute them together, so I look at the code again. So at this point, the linear curve original data, so he changed it here, so it's linear data, and then it's invert U shape, which is the shape of the quadratic curve, and then draw them together. Okay, so does it mean that these above It still maintains linearity. As for this one, I just skip it and ignore it. Then I accept this one, I execute it, and let's see, this part maintains the original data and then adds a quadratic curve and then puts these two curves together for comparison. This is what I just mentioned now. At this point, saying this text is missing, what to do. So we can switch to another one. I want to change to using a package to avoid garbled Chinese characters. Ask him to directly change it for me because this is due to the package not having Chinese fonts. So I switch to another package with Chinese fonts. So you will see if the sample I observe has only one model, which is this linear model that can be approximated. You will find that these green points cannot be approximated. Okay, let me check if he helped me switch to Plotly. Okay, he still hasn't switched it for me, so he probably wrote it somewhere else. He wrote it into Plotly to avoid garbled Chinese characters. Installed it, so now it's using installation OK, so it first installs, and after installation then, I need to check if it's executed because it only did the installation, so let me see where it installed. Here, installed, and after installation, you need to directly ask it to use it because this Plotly has Chinese execution. So we need to go to this place and ask him to change it. So I told him, here, tell him to change all the drawings to Waterloo. Afterwards, at this point, you will compare. At this point, don't blindly press accept. See what he changed. Did you see he switched packages? So after switching packages, then these. The data and model approximation, he actually doesn't need to change. What needs to be changed is the declaration and usage method of the drawing, okay? So we accept. Then, oh, I pressed the wrong button because I accidentally pressed cancel. I accidentally pressed cancel. Please redraw it for me. Okay, good then. Let's compare now. All the garbled text we had before has been resolved, and there's a small explanatory icon that appears when you approach this point. So what are we going to do now? Can we try using the framework they obtained? Look, if this framework is all bent and twisted and you insist on using linear regression to approximate it, you have to find a slope that can approximate it, but many of your predictions will be inaccurate. So it should be an irregular curve. What should we do? You can try something when you practice later, which is to pull out these different frameworks and then place them here to find not this, but replace the part where we create data with real data. Then you can interact with AI to simulate which model combination should be used for regression to best match the sample you have. If you can find the sample that is closest and the suitable model for it, then this suitable model will fit beautifully. That's why before doing machine learning, you need to be able to observe the data, and when there are only data points, be able to see with your eyes the possible existence of a certain trend, and then describe that trend with a mathematical formula. This is the initial step when making predictions. We start with data. Why do we say data can be inaccurate? It's when the distribution changes. Like here, if your sample only collects up to this point, you might think these two samples are linear, but when this green point sample starts to increase, and its original linearity begins to transform into a quadratic curve. It means the sample's curve has appeared, so its distribution is no longer the same as the original straight line distribution. So at this point, you can't use the same model. When observing data, if the data continues to increase and its distribution changes, we need to retrain. That's because your model's assumptions have started to deviate, so we need to be able to follow the different data as they are added to your observation points and deduce what possible curve, polynomial, or more complex mathematical model might exist. This is the basic ability needed when making predictions. So what practice are we going to do now? This practice is very simple, just like the previous times. If you can convert this fake data into some kind of real data, and then as your real data observation points increase, can you interact with the AI and ask it how to define the recommended model as these observation points increase, and then fit it again. To do this, I'm going to pull out the code I shared last time, just like before. This is the code I shared, and after pulling it out, I'm going to do something next. Didn't I create these two lines last time? Now, I've decided to do something if I want these two lines to become a certain type of model prediction. You can continue writing here what I want. To perform a regression model on these two investment performance lines, but I don't know which model to choose, help me observe the corresponding mathematical formula from the sample, and then let's see how it works. Because we can now observe these points and form this curve. If I want this curve to become a predictable model, it definitely isn't purely linear. It might be a U followed by another U, which is a positive U followed by an inverted U, or here is a U followed by an inverted U and then possibly combined with many cosines. So at this point, let's see, after observing, it is a nonlinear upward trend. Nonlinear means, as we said, it might be polynomial or trigonometric functions. So it's definitely not what we just mentioned, y equals x plus b. So he said it might be multiple binomial models to explain these values. So at this point, he starts to say, let's establish this quadratic polynomial. Actually, Descartes was not just a philosopher, he was also. This is simple. If you only look at the mathematical formula, without the binomial coordinates to mark this point, you wouldn't have this geometric figure. So who was the person who combined this geometric figure with the mathematical formula? It was proposed by Descartes. Now, the exercise to do is very simple. If you fully understand and previously you have worked with different data, then if we can also use this student's copy to drive, he chose the framework, not the minimal one I did before. You can also tell him here, I want to use this set of data to perform polynomial regression, please. Directly observe these data points and help me combine the corresponding mathematical model and draw this model out. It run for a bit. Let's take another look here. He said there are some errors that need correction, so I'll let it run. Let's wait for it to run. This one, run this one. So now if you learn some basic science, you have the ability to integrate it. Then when you write code, you'll feel a great sense of accomplishment because you'll know why these basic sciences were chosen and why you need to understand them. And if you read some history of science, you'll find the time and space background when it was invented quite. Okay, so at this point, it shows a trend with this upward quadratic curve, and it shows this. We need to use mean squared error. If it can be smaller, it means the model you fit is better. So this is another level of machine learning evaluation, which is how you know if the curve or model you chose is good. We accumulate the error of each prediction with its actual price. The smaller this accumulated error, the better. So this is what he came up with. He thinks TSMC fits a linear model while he believes MediaTek follows a quadratic curve. So these two are AI suggestions. You can also ask if there are others and then you can try it yourself.